All right, all you future pharmacists out there, welcome. If you're studying for your B.Pharm, you already know that the medicines you'll be working with are way more complex than they look. That's why today we're going to break down a concept you absolutely have to nail down: dispersed systems. Let's jump right in.
Have you ever really thought about that? It's a great question, right? It all comes down to the science of mixtures, and more specifically, the science of the tiny little particles hiding inside them. It's all about how one substance is scattered within another, and that is exactly what we're going to unpack today. So here's the game plan. We'll start with the basics of these unseen mixtures. Then we'll get into why particle size is everything when it comes to classifying them. After that, we'll do a deep dive into the three big categories. And to wrap it all up, we'll talk about why this is such a rock-solid foundation for your entire pharmacy career. Okay, let's start right here. You see, most of the dosage forms you'll ever dispense, I'm talking everything from syrups to creams, they aren't just simple solutions. They're what we call dispersed systems. And really, getting a handle on them is fundamental to understanding how medicines are actually made. You know, every single dispersed system has two main parts, two key players. First, you've got the dispersed phase. Just think of this as the stuff being scattered around, like tiny particles of a drug. Then you have the dispersion medium. That's the main substance that's doing all the scattering, like water or maybe an oil. It's a really simple idea, but it's so powerful. You've got particles suspended in a medium. That's it. So with all these different mixtures, how do we tell them apart? Well, it honestly all boils down to just one critical factor: the size of those dispersed particles. It sounds simple, but that one single property changes absolutely everything about how a medicine looks, how it feels, and how it behaves in the body. And that single factor gives us three really distinct classes, all based on a scale we measure in nanometers. First, you have the absolute tiniest, which are molecular dispersions. Then there's the middle ground, colloidal dispersions. And finally, you have the largest ones, the coarse dispersions. Let's take a closer look at each one. All right, it's time for that deep dive. Seriously, understanding the exact differences between these three is so crucial. It affects everything from how you formulate a sterile injection to how you create a stable cream that won't separate on the shelf. First up, molecular dispersions. In this case, the dispersed particles are unbelievably tiny. We're talking about individual molecules or ions just floating around. The result is what we call a true solution. It looks perfectly uniform, perfectly clear, because those particles are literally too small to see or to even scatter light. Let's just connect the dots on these properties. Because the particles are smaller than 1 nanometer, the whole system is completely clear. They're so tiny that they can just zip right through not only regular filter paper, but even those fancy semi-permeable membranes. Okay, so here's why this matters for pharmacy. These systems are incredibly stable. The particles are never going to settle out. This makes them absolutely perfect for any medicine that needs to be completely pure and consistent, like simple oral syrups, or even more importantly, intravenous injections. All right, next, we're moving up the size ladder to colloidal dispersions. In this category, the particles are bigger. Now, the system might still look pretty uniform to your naked eye, but if you were to look at it under a microscope, you'd see it's actually a mix of tiny particles just hanging out in the medium. And this is where we see a really key difference. With particle sizes now between 1 and 1,000 nanometers, they're big enough to get blocked by a semi-permeable membrane, even though they can still sneak through an ordinary piece of filter paper. That right there is a classic defining feature of a colloid. Colloids are literally everywhere in a pharmacy. Just think about gels, creams, and a ton of different emulsions. They also have some really cool, unique properties, like the ability to scatter light. It's called the Tyndall effect, and it's the whole reason a flashlight beam becomes visible when you shine it through a colloid. It's also why they often look kind of cloudy or opaque. And finally, we get to the heavyweights, coarse dispersions. Just like the name says, the particles here are large and in charge. This system is visibly not uniform. You can often see the individual particles, and you better believe they have a tendency to settle out because of gravity. The properties here really tell the whole story. With particles bigger than 1,000 nanometers, the mixture is obviously not uniform at all. And those big old particles, yeah, they are not getting through filter paper, period. This is the world of many oral suspensions, like that antacid we talked about at the beginning, and some topical emulsions. The absolute most critical takeaway here is that these things need stabilizers. Without them, the drug particles would just sink right to the bottom, and that would lead to totally inconsistent dosing. That's exactly why you see shake well before use on so many labels. So, we've gone through the three types. But let's get to the real question. Why is it so important for you as a pharmacy student to have this stuff memorized? Let's bring it all home and connect it to your future job. Look, this knowledge is your foundation, plain and simple. It's what helps you pick the right dosage form for a specific drug. It helps you predict how long a product is going to be stable on the shelf. It even guides you in choosing the right ingredients to keep it all mixed together. It's the core principle you have to grasp before you can really truly understand more complex stuff like suspensions and emulsions. And trust me, it does not stop here. A key thing to remember from all of your pharmaceutical science courses is that everything we've talked about today is really just the launching pad. This is the base you'll build on to understand much more advanced topics you'll see later on, especially when you get into the really complex behaviors of colloids.
So the next time you pick up a bottle of medicine, doesn't matter if it's crystal clear or milky white, I want you to just stop and think about what's happening inside on a particle level. Ask yourself, what kind of dispersion is this? And what does that tell me about how it works and why it was made this way? Thanks for tuning in.